Hello everybody. In this video, we are going to go through some of independent random variables. In other words, we are going to convolute two functions. This is example 1. Suppose x is exponential with parameter lambda and y is exponential with parameter kappa. Lambda is not equal to kappa and x and y are independent variables. Let z be x plus y. Find the PDF of z. PDF of z is the convolution of fx and fy, and convolution by definition is integral from negative infinity to positive infinity, fx of s, fy of t minus s ds. So let's start with the definition of convolution. Convolution is, as we said, is the integral from negative infinity to positive infinity, fx of s, fy of t minus s ds. Here, fx of s is our x exponential random variable. So we need to know the density function of exponential random variable. X exponential with parameter lambda has this density function. The density function is 0 if the variable s is less than 0, and it is lambda e to the negative lambda s if s is greater than 0. And this is the graph of the density function. It is 0 up to 0 and some decaying exponential function from 0 to infinity. So this density function is supported from 0 to infinity, and the top point of the graph is the lambda. Now we're going to place f of x s with the density function lambda e to the negative lambda s, and we're going to change the limits of integral from 0 to infinity because the function is supported from 0 to infinity. So we can change the limits of integral from 0 to infinity instead of negative infinity to positive infinity, and f of x s will be lambda e to the negative lambda s, and we have fy of t minus s ds. Now we're going to use substitution for t minus s. Let u be t minus s. Then du will be derivative of t minus s with respect to ds. So derivative of negative s is negative 1 ds. Also here solve for s because we're going to use it. So s is t minus u. Now let's place everything in terms of u. Now we have integral from 0 to infinity. We have lambda e to the negative lambda. Instead of s, we're going to write t minus u. And we have fy of, instead of t minus s, we're going to use our u substitution. And instead of the s, we're going to use negative du. So we can write du here and pull negative sign to the front. Since we have written everything in terms of u, we also have to change the limits of integration. So when s was 0 at the previous integral, the u was t. So our new limits of integral will be t. When s is 0, u is t, and when s is infinity, then u is negative infinity. So here when s is 0, u is t, and when s is infinity, u is negative infinity. So we change the limits of integral in terms of u as well. Lambda e to the negative lambda t minus u, fy of u du. And we had negative sign here. Now our lower boundary of integral is greater than the upper boundary of integral. So we need to switch lower and upper boundary and negate the integral, which means we're going to multiply the integral by negative sign again by changing the limits of integral. And negative times the negative in front will be positive, and negative infinity to t. Lambda e to the negative lambda t minus u. Now let's figure out fy. Here exponential function y with the parameter kappa has this density function 0 if t is less than 0, and kappa e to the negative kappa t if t is greater than 0. And this means that is the integration under the area under the curve from 0 to t dt, because this is the graph of the exponential y density, and when we are finding the t here, we are integrating the area under the curve, and that is from 0 to t. So instead of fy of u, we're going to use this density function. Okay, so our new integral will be negative infinity to t lambda e to the negative, we can distribute this, negative lambda times t, and negative lambda times negative u is lambda u. And the density function of fy of u will be kappa e to the negative kappa u, and we have d. Now we're going to integrate this integral. We can pull out lambda kappa and e to the negative lambda t, because all we are carrying is the u variable. So our new integral will be lambda times kappa e to the negative lambda t, and integral from, and we need to change the limits of integration again from 0 to t, because it is supported from 0 to t for exponential y. And we can merge this e's, so e to the u times lambda minus kappa du. So we have lambda kappa e to the negative lambda t, and antiderivative of this function is 1 over lambda minus kappa times e to the u times lambda minus kappa, evaluated from 0 to t. So we have this function times upper boundary is e to the t times lambda minus kappa, minus lower boundary will be e to the 0, which is 1. So this function times upper boundary minus lower boundary. So our function will be lambda kappa over lambda minus kappa, and if we distribute this into the e, we're going to obtain e to the negative kappa t minus e to the negative lambda t. So this is our density function for z. Let's rewrite. So density function for fz of t is 0 if t is less than 0, and it is this function we found, the first parameter times second parameter over lambda minus kappa e to the negative kappa t minus e to the negative lambda t if t is greater than 0.